Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The Riemann-Roch theorem is an extremely useful tool in algebraic geometry. And in this video, I want to give you an application of the Riemann-Roch theorem to studying low genus curves. In fact, we'll be able to classify all the curves of genus 0 and 1. Okay, so let's see how this works. So consider x here. In this video, will always be a smooth projective curve, and we'll work over the field K, which is algebraically closed. And as usual, we'll let G denote the genus, some old notation. Omega x will denote the canonical sheaf, and Kx will be a canonical divisor. So this is basically any divisor such that if you look at O of this Kx, it's isomorphic to this canonical sheaf here. Okay, so let's look at the case where the genus is equal to 0. Genus is equal to 0. So another way to characterize this by Riemann-Roch, and I'll just remind you how this works later, is negativity of this canonical divisor. So the degree of this canonical divisor is less than 0. So if we have this, then we actually know exactly what this x is. X, up to isomorphism, is just a projective line. That's rather nice, isn't it? Okay, so let's see why that's true, and the proof is actually very short. Okay, so firstly, just to remind ourselves, what's the relationship between the canonical divisor and the genus? Okay, so the degree of the canonical divisor is just twice the genus minus 2. Okay, so note that the genus here, okay, it's always going to be an integer which is at least 0. Okay, so it's the dimension of the global sections of this, or h1 of O. Okay, so it's always going to be at least 0. So the only time this can be negative is when g is equal to 0. Okay, so that's why these two conditions here are equivalent. Okay, so when g equals 0, it will actually be minus 2. Okay, so what we're going to do is we're going to look at O of P. We're going to try to map, okay, this x into projective space using sections of an invertible sheaf. And the invertible sheaf will pick as O of P, where P is just any single point on x. Okay, so let's do that. So if you want to do that, what we're going to do is we need to know about this space of global sections of this. So we want to look at little h0 of that. And Riemann-Roch theorem tells us about chi of that. And one way to express of chi is it's h0 minus h1. So h0 of this is what we want to look at. And h1 we can use, we can approach using Serre duality. So Serre duality rewrites that as h0 of k minus p. And in this case, we have an effective vanishing here. This is going to be 0. And the reason for that is, what's the degree of this divisor here? Well, k is minus 2, degree minus 2. So, and then when you subtract p, that becomes degree minus 3. Since it's a negative degree here, the h0 has to vanish. Okay, so that's rather nice that in this case, here the chi, which is really what the Riemann-Roch tells us, actually gives us what the value of h0 is. Okay, so what's this Riemann-Roch tell you? So the formula is 1 minus the genus plus the degree of this divisor here. Okay, so the genus here is 0, so it's 1 minus 1, and the degree of p, there's a single point, so you just add 1. So this is equal to 2. And we know that, well, if you have a line bundle, an invertible sheaf of degree 1, and it has two linearly independent sections, okay, you can use those two linearly independent sections to map to P1. They're the homogeneous coordinates, say x and y on P1. And that will actually be an embedding because you're using a degree 1 invertible sheaf. Okay, so that gives you the isomorphism between x and P1. Rather neat, isn't it? Okay, so we've disposed of the case where the genus is equal to 0. What about the case where the genus is equal to 1? Well, these are often called elliptic curves, although some people like to be a bit more precise. An elliptic curve is a genus 1 curve with a chosen distinguished point. Okay, so let's just give a little example so that we can get some feel of what's going on here. So suppose your smooth projective curve x is also an algebraic group. Okay, so what does it mean to be an algebraic group? So that means, well, it's got to be a group. So if you look at all the k points of this x, okay, it has a group multiplication. So you can map from x cross x to x. So this is going to be a group multiplication. So it has satisfies the group axioms such as associativity in particular. But this is also a map of varieties of in this case, x is a projective curve, so this is a projective variety as well, so it's a map of projective varieties. And we want this map to be regular as a map of projective varieties. Okay, so it's a morphism of projective varieties. Something else that we also need is that when we have a group, remember you can, all elements have inverses. So we want to think of this inverse as a map from x to x. You can send an element little x inside big X to its inverse. And we want this to be a regular map as well, so a morphism of projective varieties as well. And if these two conditions hold, okay, then we have an algebraic group. Okay, and in this case here, the genus will equal 1, and there is a chosen distinguished point. Okay, there's a natural one because this is a group. It has a group identity 1x. Okay, so that's one of the reasons why we consider things with a distinguished point. Okay, so let me just tell you why this is true. Okay, and the reason is as follows. Remember the group structure. Okay, is going to tell us something about the canonical sheaf. Okay, it tells us the canonical sheaf is trivial because basically you can take the tangent space of x at the identity and you can use the group structure to translate that tangent space to any other tangent space on this x. And that allows you to trivialize the tangent bundle there. And hence the cotangent bundle, which is essentially this omega x, is also trivial. Okay, so since this is isomorphic to O, and this is giving us the k, the degree of this k is just the degree of this, and the degree of O, of course, is just 0. So we have the degree of k is equal to 0. And remember, the degree of k is also written in terms of the genus as 2g minus 2. So if you solve 0 equals 2g minus 2, of course, the solution is g is equal to 1. So the genus is 1. Okay, so that's rather nice that in this case here, this algebraic group structure, okay, allows us to give us this, determine the genus. Okay. So what's the theorem about these elliptic curves? So let x be an elliptic curve, so just a genus 1 curve, and then we can pick any point P in this x. Okay. Then what can we say about this? Well, then x actually embeds inside P2 as a cubic curve. So firstly, this curve, it's a plane curve, okay, or it's isomorphic to a plane curve. Not all curves are such that they're isomorphic to some curve inside the plane, okay, but it is actually isomorphic to a curve inside P2, so it embeds inside P2. And you can say a little bit more about that. So how does it embed inside P2? Well, it's given by a single cubic equation inside P2, and that's rather nice, okay. So that means that really you can think of it as something that's very familiar, okay. You have P2, and you can just think about all the solutions to some cubic equation inside there. And what's rather nice is you have a converse to this example, really, okay? So furthermore, this is actually a commutative algebraic group. And so since it's commutative, we'll use a 0 instead of a 1, okay? And where can you put the 0? You can assume the 0 is at P. So this is rather interesting, actually, if you think about it, because this was an arbitrary point of x. So if you change this P, you'll get a different group law on it because the 0 will be different. Okay, so you'll have one group law for every point on there. Okay, so let's look at the proof of this theorem, and it's a really, really beautiful application of the Riemann-Roch theorem. Okay, so let's look at Riemann-Roch. It's telling us about basically the Euler characteristic of invertible sheaves of the form OD, okay, and that will give us a handle on H0 of OD. And the time when it's most useful is when the chi is equal to the little H0. This is something I can't stress enough, okay, and for that you need a vanishing of H1. So the instances that we'll look at is where the degree D here is a divisor, this divisor D is a divisor whose degree is positive. And the reason why that's the case is if it's positive, remember the degree of k we saw here, the degree of k is equal to 0. So that means the degree of D is bigger than the degree of k. And then Serre duality is going to tell us that the H1 of this O of D is equal to 0. Okay, so Serre duality is a very effective way to get a vanishing of H1. And this is extremely important. Okay, so in general we know that with Serre vanishing, if you have a divisor of high enough degree on a curve, then H1 will vanish. But you want to have some actual bound on how big that can be. And in this case here, the actual bound is it just has to be bigger than 0. Okay, so it's really effective in that way. Okay, so what's Riemann-Roch tell you? So the little h0 here is the same as the Euler characteristic chi of OD. And this chi, we have Riemann-Roch, which tells us what this is. And the formula is, again, 1 minus the genus of the curve plus the degree of D. So the genus is equal to 1, so this 1 minus g term here is equal to 0. And so this is just equal to the degree of D. So the dimension of the space of global sections of OD is just the degree of D. Okay, so that's rather nice. Okay, so before, what we did was we looked at O of P, and we looked at sections of that to map to P1, and that will give us our isomorphism. Now we want to map to P2. Okay, so we're going to use some sections of some invertible sheaf, and what invertible sheaf is that going to be? So the invertible sheaf that we want to do now is, again, we've got this chosen point P here. We're going to do something similar, but we're not going to use OP, we're going to use O3P. Okay, we'll see in a minute why that's true. Okay, H0O3P. Now you can think of this, these global sections in lots of different ways. The way I want to think about it here in this proof is that this is the space of rational functions on this X, which have only poles at P, and the order of the pole is at most 3. Okay, when you think about that, this obviously contains H0O2P, since these are just the rational functions whose only pole is at P and the order there of the pole is at most 2, and that in turn contains H0 of OP, which in turn contains H0 of O, and the only global sections of O, so the only functions which are globally defined and regular everywhere are just the constant functions K. Okay, so that's great, and again, the thing here is to use Riemann-Roch, so we're going to use Riemann-Roch, okay? So this here, the divisor here, 3p is degree 3, so the dimension of this is 3-dimensional. This here is degree 2, divisor here, so this is 2-dimensional. This is 1-dimensional, this is also 1-dimensional, so these are actually equal. Okay, so let's start picking some sections, okay? So here, this is 3-dimensional, we can find three linearly independent sections, but we'll do this in a fairly particular way. So the first thing is that we'll start down here. This is 1-dimensional. We can just pick the constant 1. Okay, this is still 1-dimensional, so you won't get anything extra until you come up to here. When you come up to here inside H0O2P, you can. This is 2-dimensional, so you can find something that's linearly independent from this constant. Okay, so we'll pick any element, call it V, and it won't be inside here, which tells you what? It tells you that it has a pole of order 2 at P. So the divisor of V is equal to minus 2p plus some positive stuff. So it'll have 2 zeros when you count it with multiplicity somewhere else. Okay? So that this 1 and this V will span this 2-dimensional space of global sections. And then you go up to here, this is 3-dimensional, so you can find something, say U, which is linearly independent from that V and that 1 again. And since it's linearly independent from that V and that 1, it's not inside here, okay? So the divisor of this is going to be minus 3p plus some, where the 3 zeros are, okay? So in other words, this is a triple pole at P, okay? This is a double pole, and this is just a 1, okay? So that's going to be what we're going to use. We're going to use these 3 sections, and that's how we're going to map X to P2. Okay, so basically it's going to send the point X to, remember U and V are rational functions, so it will just be U of X colon V of X colon 1. Okay, so the 1 might look a little bit funny here, but remember we can scale these rational functions because you're working with homogeneous coordinates, so you can scale them. Okay, so another way to think about this is that where these U and X and V of X are defined, okay, you're mapping into that affine patch where this last coordinate is non-zero. Okay, great. So that's what we've done here. And I guess what do we need to do? So at least we have a map to P2. And we know since these are rational functions and they're not constants, right? They're not inside here, right? That this is going to be a mapping onto, this is a non-constant map to P2. Okay, so furthermore, this is the image of a projective variety, so it's going to be closed inside P2, and it's not constant, and it's connected, so it's going to be some sort of curve inside P2. And so the main thing to show is that, well, why is it a cubic curve? Okay, so one thing that Riemann-Roch has already allowed us to do is it has allowed us to come up with a non-constant map to P2, and it's also going to now tell us how you get that map maps it to some cubic curve inside P2. So let's see how that works. And the way we'll do that is we're going to look at O6P. So what we can do is we can continue this sequence. We can look at O4P, O5P, and then up to O6P. So O6P, this divisor here, 6P is of course degree 6, so this is 6-dimensional. Okay. So remember, this contains all of these. Okay, so it will contain the 1, the V, and the U. It also contains O4P. Okay, so that's the space of divisors with a 4-fold pole at P. But one way to get a 4-fold pole at P is, well, V has a double pole at P, so if you look at V squared, okay, that's going to give you a 4-fold pole at P. Okay. Then we can look at, so these are linearly independent, 1 V, U, and V squared. Then you can go up to H0 of O5P. Now if you multiply U and V, that's going to be O5P. In O5P, because that's going to have a 5-fold pole at P. Okay. And finally we can look at O6P, and how can we get elements in there? Well, one way is you can take this function V with a double pole at P and cube it to get V cubed. And another way is you can take this function U, which with a triple pole, and square it to get U squared. Okay. And then let's see what happens here. Inside this 6-dimensional space, you have 1, 2, 3, 4, 5, 6, 7 elements. So that's telling you that there has to be some linear relation amongst these elements here. Okay. This is from Riemann-Roch. We know this is 6-dimensional. It's not 7-dimensional. Riemann-Roch tells you that it has to be 6-dimensional. Okay, so there has to be a relation between them. And it's quite easy to see what the relation has to be of the form. Well, you have to use the last two, right? So it will be V cubed equals some of these other ones here. And what you'll see here is exactly, well, that's a cubic relation, right? Okay, so it's a cubic relation. And that gets you your the cubic relation, and the fact that the image of this map phi is actually a cubic curve. Okay. So by the way, I should mention that I learned this argument from my supervisor, Michael Arden, who is one of the great algebraic geometers. Okay, so I guess to complete the proof, we need to do two more things. So firstly, we have to say, why is this map an embedding? Okay, that's the first thing. And the second thing is to talk about the group law. Okay, so why is it an embedding? So I guess the most important thing is that if you take 2 points inside this X, okay, they get mapped to different things. Okay, so let's make sure that we can separate, using this map phi, any 2 points Q and Q prime in X. Okay, so let's do that. So what do we need to do? So basically what we'll do is we'll look at, we just have to find some linear combination of these functions, okay, which takes different values at Q and Q prime. Okay, that's what we're going to do. And how are we going to get that? So how are we going to get a linear combination? So linear combinations of these, of course, remember these three form a basis for this H003P. So we're going to look inside here, okay? So inside here, what we can do is we can look at all the rational functions, okay? So this is a space of rational functions with at most a triple pole at P. But we'll look at those ones which actually have a 0 at Q. And we'll also look at this, inside that, we'll look at the ones which not only have a 0 at Q, but also have a 0 at Q prime. Okay? So if you look at this, well, what's the degree of this? This is 3 minus 1 is 2. And Riemann-Roch tells us that this is 2-dimensional. We look at this, what's the degree of this? 3 minus 1 minus 1, that's 1. So this is 1-dimensional. So that means that you can find a section that's inside here, and that's not inside here. Pick such a section, and basically this section is going to be 0 at Q, and non-zero, since it's not here, it can't be 0 at Q prime as well. So it's going to be non-zero at Q prime, and so using that section, which is a linear combination of these three, you'll see that that will separate those 2 points. Okay, so this is the key thing. Okay, so you can separate 2 distinct points. Actually, to show that it embeds, it's a little bit more subtle than that. Okay, so one of the things that you need is that you really want, so to speak, like a diffeomorphism. So you really want to make sure that you have an isomorphism on tangent spaces as well. And one way to do that, and this is the wonderful thing about the way algebraic geometry is set up, is that you can think of this as saying, to say that you have an isomorphism on tangent spaces is basically saying that you can separate tangent vectors. Okay, so, well, that's what you call it, separate tangent vectors. And separating tangent vectors basically corresponds to the case where q equals q prime. Okay, you let the 2 points come together, and as they come together, that essentially defines a tangent vector. Okay, and so if you apply this argument, it turns out that if you apply the argument with q equal to q prime, then this shows that you can, so to speak, separate tangent vectors too. So you have an isomorphism on tangent spaces. So this really gives you an embedding. Okay, so it's rather nice. Again, Riemann-Roch comes to the rescue and does what you want. Okay, then the last thing, which is also another application, wonderful application of Riemann-Roch, is to get the group law. Now, this group law you can get from the fact that just that it's a cubic curve. You can show directly from the fact that it's a cubic curve that every cubic curve is has a group law. But it's actually easier to do it directly using Riemann-Roch. And let me show you how that works. Okay, and it comes from the following lemma. So let's look at this lemma. So we're going to construct a map from X to a group, and that group is just the Picard group of degree 0 divisors on X. Okay, so pick 0 of X. So it's the degree 0 divisors modular linear equivalence, or if you like, the degree 0 invertible sheaves on X. But we'll think of this pick 0 as divisors of degree 0 up to linear equivalence. Okay, so when you do that, if you take a point Q inside X, you can get a degree 0 divisor by doing Q minus P. So you can see here why it's important to have picked a point. Okay, so that's kind of part of the data. Okay, and you can pick whatever point you like, but you fix that, and once you do that, you look at this. Okay, so this is certainly degree 0, and the point is this is a bijection. And once you know this is a bijection, you see, you can use pull the group law back on here back to here. And it'll turn out that this will actually make it, it'll be algebraic, make this X an algebraic group. So the group addition in this case is actually going to be a regular map, and so the group negation is also a regular map. Okay, so let's see how this works. So I guess we just have to show it's surjective and it's also injective, and we'll use Riemann-Roch actually to do both, although the second part doesn't really require Riemann-Roch, strictly speaking. So let's start with something on this side. So we have some divisor D, which is degree 0. Okay, and we want to study that divisor. Okay, so we have something over this side, and we want to say it looks like a Q minus P. So basically, we want to solve for the Q. Where does it come from? So we're going to add P to it. So we look at D plus P. Look at O of D plus P and say, what's the global sections of this? Okay, what's the dimension of the global sections? Well, what's the degree of this? The degree is 1, which is positive. So Riemann-Roch in this case, remember here, Riemann-Roch actually tells us exactly what this H0 is. It's 1. Okay. Now remember, what is the global section? So one of the ways to think about the global sections here is that up to scalar, the elements here correspond to effective divisors linearly equivalent to D plus P. And since this is dimension 1, okay, all the non-zero elements are scalar multiples of each other. So there's actually just a unique effective divisor that's linearly equivalent to T plus P. And since it's degree 1, that has to be a point Q inside X. So there's a unique Q with Q linearly equivalent to D plus P. And that tells you it's surjective, and really it tells you it's injective too. So if you want to see more strictly speaking, why is it injective? If Q minus P, if you have Q and Q prime here, which map to the same thing, so Q minus P is linearly equivalent to Q prime minus P, then of course you can add P to both sides. Q is linearly equivalent to Q prime. And this argument here, H0 of OQ equals 1. Remember, this means that there's a single effective divisor linearly equivalent to this, it gives you this OQ, okay, so that's linearly equivalent to Q, and that of course is Q itself, so Q and Q prime have to be equal. And that completes the proof of, essentially, of the group law, that constructs the group law on X. Okay, so we've seen various ways that Riemann-Roch can be applied to study low genius curves here. The key thing is that it allows to really tell you about the dimension of the global sections of invertible sheaves. So you can use those to try to map it into projective space. And it gives you enough control that it can really tell you a lot more about what's going on as well. So we can easily see, for example, in this case of elliptic curves, that we get a cubic equation. I hope you enjoyed this adventure in pure mathematics.